Good afternoon, students. In the last class we have completed a polytropic process, that is PV to the power of n is equal to constant, where n is the index. So in that process already we have completed two problems. So today we will work out some 2 or 3 problems. So in that the first problem is 1 kg of steam of dryness fraction 0.96 is expanded according to PV to the power of n or PV to the power of 1.02 is equal to constant. So the value of n is 1.02. The pressure has been reduced from 20 bar to 1 bar. That means the initial pressure is 20 bar and after the process the pressure is 1 bar. Determine final condition of steam, work done and change in internal energy by taking Cp is equal to 2 kilojoules per kg Kelvin. Okay, it is a polytropic process, that is PV to the power of n is equal to constant. So I have taken values for initial pressure of 20 bar and final pressure of 1 bar. The Vg, Hf and Hfg value I have taken from the steam table. So first we should find the final condition of steam. So before that, so observe the dryness fraction value, it is 0.96. Therefore the initial condition of steam is wet with a pressure of 20 bar. So final condition is not known, for that we have to find the value of x2. So in a polytropic process, x2, the final condition dryness fraction of the steam, that is x2 relation is x1 Vg1 by Vg2 into P1 by P2 whole to the power 1 over n. So substitute all the values x1 Vg1 Vg2 and P1 P2 values. So you will get so the final dryness fraction is 1.062. See, the value of final condition of the steam or the value of dryness fraction after the process is more than 1. Therefore the condition of steam is superheated. Now initially it is a wet steam because dryness fraction is given, after it is superheated steam because the dryness fraction is more than 1. Now, so the relation what you have taken here, assuming both the conditions are wet, that means initially and after, now it has replaced like this, because here see here P1 x1 Vg1 to the power of n is equal to P2 V sub to the power of n I have taken. Why? Because the final condition of steam is superheated. So now you find V sub 2 first, substituting the values you are getting V sub 2 is 1.8 meter cube per kg. Why we want V sub 2? Because the final condition is superheated. So we have to find the superheated temperature or degree of superheat. Therefore you must find this V sub 2. Next, so therefore T sub 2 is equal to T2 into V sub 2 divided by Vg2. You got T sub 2 is around 123 degree C. It is a superheated temperature. Suppose you want a degree of superheat, that is degree of superheat is what? Always T sub minus T sat. T sub is 123 and T sat is 99.6. The difference of this is your degree of superheat. This you must find. So now work done. So we know both the conditions now. Initially it is wet and after it is superheated. So what is the work done formula? Work done W is equal to 10 square or 100 P1 V1 minus P2 V2 divided by n minus 1. So initially I have taken x1 Vg1 because it is wet steam. After the process I have taken V sub 2. In place of V2 I have taken V sub 2 because the final condition of steam is superheated. So now I have all the values. So P1 is known, x1 is known, Vg1, similarly P2 and V sub 2. So we are getting the work done is around 552 kilojoules per kg of work done is done on the system. Next, change in internal energy we want, that is change in internal energy is nothing but delta E is equal to final internal energy minus initial internal energy. Initially it is wet, finally it is superheated. So we know the conditions. Therefore first I must find E wet 1. What is the formula for E wet 1? E wet 1 is equal to H wet 1 minus W wet 1, that is HF1 plus X1 HFG1 minus work done is 10 square P1 X1 Vg1. Substitute all the values, then you will get the internal energy. Initial internal energy of wet steam is around 2530.8 kilojoules per kg. After that, final condition is superheated, because dryness fraction we got 1 point something. So what is the internal energy of superheated steam? H soup minus W soup. So H soup formula is here, HF2 plus HFG2 plus T soup Cp into T soup minus T sat minus W soup is 10 square P2 V soup, because it is a superheated steam. So substitute all the values, so you will get around 2542.3 kilojoules per kg of internal energy after the process. Therefore, change in internal energy delta E is equal to always the final condition minus initial condition. Finally, we have 2542.3 kilojoules per kg and initially around 2530. Therefore, the change in internal energy is just 11.5 kilojoules per kg of change in internal energy takes place between initial and final condition. So next, sixth problem, it is also on a polytropic process. 1 kg of steam at a pressure of 15 bar and 300 degrees C. Initial condition of the steam is superheated, because temperature is given around 300 degrees C. Expands according to the law PV to the power 1.25 is equal to constant. The value of N is 1.25 to a pressure of 1.5 bar in cylinder. Determine 3 parameters you should find: final condition of steam, work done, change in internal energy by taking Cp again 2 kilojoules per kg Kelvin. So 2 pressures are given. In that, initial condition we know, that is superheated, and final condition is not known, the pressure is known. Therefore, from the steam table you take values for initial pressure and final pressure, that is 15 bar. We have taken Vg value, here HF value I have not taken, directly HFG value here I have taken. Next is, because it is a superheated steam, next final condition is 1.5 bar, I have taken Tsat value, Vg value, HF value and HFG value. So after taking the values from the steam table, first we should find the final condition of steam. Initially it is superheated and finally we do not know, but we should assume always, if the condition is not known, final condition is a wet steam. So I have used this relation. See here, P1 V soup 1 to the power n. Why I have taken V soup 1 initially? Because the initial condition of steam is superheated. It is given in the problem. Next, finally I have taken P2 V2 Vg to the power n. Why I have taken x2 Vg2? Because final condition is not known, even though we are assuming that the final condition is wet. Therefore, we are taking always wet formula. So here x2, you get x2 by substituting all the values, simplifying the relation, you are getting x2 value is, observe here, 0.919. It is less than 1. Therefore, the final condition of steam is wet. Now it is clear, initially it is superheated and final condition is wet. So first, always in all the problem you must identify these two conditions, initial condition and final condition, then only you can work out the problems. So in the problem you want final condition of steam as well as, right? Okay. So next is work done. Work done is equal to, we know W is equal to, in a polytropic process, 10 square P1 V1 minus P2 V2 divided by n minus 1. What is the initial condition of steam? Superheated. Therefore, P1 V soup 1 minus P2 X2 Vg2. Why? Because final condition is wet and initial condition is superheated. Therefore, I have taken this relation. By substituting the values, you will get around work done is 374.32 kilojoules per kg. Next, change in internal energy in a polytropic process, that is delta E is equal to final condition minus initial condition. Final condition of steam is wet, initial condition is superheated, therefore change in energy delta E is equal to E wet 2 minus E sup 1. First find E sup 1. E sup 1 is nothing but H sup 1 minus 10 square P1 V sup 1. So observe here, this H sup 1 you can use this formula also, HF plus HFG plus Cp T sup minus T sat. This we have used in all earlier cases. This you can use, or directly you can take the value of H sup from the steam table. The third column in enthalpy, enthalpy of steam, that is directly also you can take from the steam table only for superheated steam, right. So that I have taken 3037.6 from the steam table directly. After that 10 square P1 V sup 1, you will get around 2784.1 kilojoules per kg of internal energy. Next, internal energy of steam after the process. After the process you got X2 is how much? 0.919, therefore it is a wet steam. So I have used a wet steam formula for internal energy, that is HF2 plus X2 HF2 minus the work done of wet steam is always 10 square P2 X2 Vg2. You have all the values, substitute the values, you will get internal energy of wet steam after the process is 2353.3. Therefore change in energy delta E is equal to E wet 2 minus E sup 1. Final condition minus initial condition, you are getting around, see here it is minus 430.8 kilojoules per kg is the change in internal energy, because initially it is superheated, which got more temperature and more pressure in the steam. After the process it becomes wet steam, the quality has reduced, therefore the some amount of, that is some means 430.8 kilojoules per kg of heat is rejected from the steam. So the superheated steam becomes a wet steam, therefore it is a negative. So like that in a polytropic process you can work out the problems. Simple relations are one relation for X2, that is final dryness fraction, that depends upon the condition of steam before and after the process. After that work done, that is 10 square P1 V1 minus P2 V2 divided by n minus 1, and change in energy is similar to all the processes, that is delta E is equal to final condition minus initial condition. So these are the problems in polytropic process. So next we will go to the last process in vapor processes, that is a throttling process. So what is actually throttling process? The steam is said to be throttled when it passes through a narrow opening or slightly opened valve, that is like a nozzle, small opening. When the steam passes through a small opening or through a nozzle, then it is called a throttle, or that process is called a throttling process. Simply you can say passing of steam through a small passage is called throttling process. So in throttling process what happens? In this process the enthalpy, is also called total heat of steam, remains constant before and after the process. That means before the process, say enthalpy is 100 kilojoules per kg, it passes through a small opening. After passing, after throttling, after process, the enthalpy is remains same. There also the total heat or enthalpy is 100 kilojoules per kg. That means in a throttling process enthalpy remains constant before and after the process. So this process is also known as wire drawing process. Why it is called wire drawing process? Means if you pass steam through a small opening, the outcoming or the steam coming out is like a small wire, because you are passing through small opening, therefore that is called a wire drawing process. So in this process, these points are very important here. In a throttling process enthalpy remains same, but see in this process no heat is supplied or rejected, therefore heat transfer Q becomes 0. Next, no work is done by expanding the steam, therefore our amount of work done is also 0. No change in internal energy of the steam, delta E is also 0. See, everything is 0. According to first law, actually Q is equal to delta E plus W. So in throttling process all are 0, Q 0, W 0 and delta E is 0. But the enthalpy remains the same before and after the process. It is a very simple process, all becomes 0. Therefore, no derivation here because all are 0. But see here, in this process, enthalpy before is equal to enthalpy after, that is H1 is equal to H2. The H for enthalpy, enthalpy 1 is equal to enthalpy 2. If the steam is wet before and after the process, we should take like this: H wet 1 is equal to H wet 2 because both the conditions are wet. Enthalpy of wet steam before is equal to enthalpy of wet steam after. What is enthalpy for wet steam formula? This we have used so many times. Hf1 plus x1 hfg1 is equal to enthalpy after, that is a wet steam, hf2 plus x2 hf2. This is the relation if both the steams are wet. Suppose if the steam is dry after the process, after throttling process, initially we have taken wet, and after the process if it becomes dry, then your relation becomes like this: hf1 plus x1 hfg1, this is for wet, is equal to for dry hf2 plus hfg2. No x2 here because it is a dry steam, right. Next, if the steam is superheated after the process, that means initially it is wet only, after it becomes superheated steam, then the relation becomes like this: hf1 plus x1 hfg1, this is for wet, is equal to hf2 plus hfg2 cp t sub 2 minus t sat 2 for a superheated. So like that, in the problem depends upon final condition or initial condition, you should take the relation like this. Suppose initially it is superheated. In some problems initial condition is superheated, after that finding dryness fraction, we will decide that whether it is dry or superheated. In that case, here first you take a superheated formula, then you take a wet formula. So depends upon the condition, you can interchange H1 and H2. This is the enthalpy before and after in a throttling process. So the important in throttling process is Q is equal to 0, W is equal to 0, delta E is equal to 0, only the enthalpy remains same before and after. That means my intention is only enthalpy formula comes in throttling process, no other formulas are there. Okay. First problem, simple problems on throttling process. So 1 kg of steam at a pressure of 14 bar and 0.9 dry. So this is the initial condition of steam. What is the initial condition now? It is wet steam. Next, is throttled, the process is given. So throttle means passing of steam through a smaller opening. 2, 1.4 bar. So this is the final pressure, but final condition is not given. Calculate final condition of steam. So we have to find the final condition. Initially it is wet and final we don't know, we will find that. So what is the initial pressure is 14 bar, final pressure is 1.4 bar. You take the value of HF and HFG. Now we know that in a throttling process enthalpy before is equal to enthalpy after. Like that also you can take H1 is equal to H2. But H1 we know that is a wet steam, is given in the problem. H wet 1 is equal to, final condition is not known. I already told you so many times. So if final condition is not known, you should take that is also wet steam. So like this you should take H wet 1 is equal to H wet 2. Substitute HF1, X1 is given, HFG from the steam table, and HF2 steam table, X2 is not known, and HFG2 from the steam table. So you will get X2, that is final dryness fraction. Substituting the values, we got 0.96. Now what is the final condition of steam? That is a wet steam because X2 is less than 1. So like that you should decide or you should find the condition of steam by using this relation. So next is second problem. Steam at 10 bar and 0.9 dry is throttled to 2 bar. Initial condition 0.9 dry and 10 bar, that is wet steam, is throttled to final pressure of 2 bar. Calculate final condition of steam and estimate the change in entropy during the process. Entropy also we should find in this problem. it is similar to previous problem. The addition is entropy. Okay, so initially it is H1 is wet steam because dryness fraction is given, final condition is not known, but we should assume that is also wet, right. What is the process? You take the value from the steam table, HF, HFG, SF and SFG also I have taken. Why? Because we want the entropy, right. In the throttling process, H1 is equal to H2, that is enthalpy before is equal to enthalpy after. Before is a wet steam, I have taken wet steam formula, HF1 plus X1 HFG1 is equal to H2. Final condition is we are assumed that it is a wet steam, so I have taken a wet steam formula. So we got X2 is this one, and substitute all the values. So you will get the value of X2, the dryness fraction after throttling is 0.94. It is less than 1. Therefore the condition of steam is wet. So initially is also wet, finally is also wet. If it is more than is exactly equal to 1, the final condition is dry. If it is more than 1, then the final condition of steam is superheated. Next, to change in entropy he want. So initially it is wet, finally is also wet. We got dryness fraction, that is 0.94. Therefore both the conditions are wet. Therefore change in entropy delta S is equal to final entropy minus initial entropy. So first you find initial entropy. What is that? S at 1. That is the formula is SF1 plus X1 SFG1. It is the initial entropy of wet steam around 6.14. Final condition of steam is wet. The formula is S wet 2 is equal to SF2 plus X2 SFG2. You substitute all the values, you will get around 6.79 kilojoules per kg K. So now therefore change in entropy delta S is equal to final condition minus initial condition, you will get around 0.65 kilojoules per kg Kelvin of entropy changes. So in throttling process normally final condition they will ask, otherwise they will ask this change in entropy. So next, third problem. First two problems we have completed. In that problems both the conditions are wet steam initially and after the process. Now come to third problem. Steam at 14 bar with 80 Kelvin of superheated. Kelvin of superheated. So 80 Kelvin of superheated. So this is important. I already told you degree of superheat. In the last 2-3 problems we have already completed. So degree of superheated means T sup minus T sat is together is equal to 80 Kelvin. No need of adding 273 because Kelvin is given. So this is one important here. 80 degree of superheat is given 80 Kelvin. Is throttled to a pressure of 8.5 bar. So this is the second pressure and this is the initial pressure. Now what is the initial condition of steam in this problem? Degree of superheat is given, so no problem. So initial condition H1 is nothing but H sup. Why? Because it is superheated, degree of temperature is given. Next, final pressure is given but condition is not given, so that we always we must consider that is a wet steam because condition is not known. So initially it is superheated, finally it is a wet steam. By using this relation you should start finding the details. What he want? Determine. So here he don't want a final condition of steam, he want the temperature of steam after throttling. So before is degree of superheated is given 80 degrees K, but after he wants temperature of steam, not condition of steam. So how to find, how to work out this problem? That means, so first you find initial enthalpy of steam, that is superheated steam, that is H sup 1 we are taking, that is Hg1. See here also directly I have taken Hg1. This value you can take from the steam table directly, that is enthalpy of steam. Observe here, third column on enthalpy after HF, HFG, the third column is Hg, that is direct value, that is a enthalpy of superheated steam. Directly you can take 2787.8 plus Cp into degree of superheat. In place of T sup minus T sat, I have taken 80. So that means, so we got because see here again, because T sup minus T sat is 80, so initial enthalpy of superheated steam is 2963.8 kilojoules per kg. This is part 1. That means we got enthalpy initially. Now final enthalpy of superheated steam. Why I have taken superheated? Because he want temperature. So only in a superheated steam condition we have a temperature, because wet steam and dry steam both are takes place at a constant temperature, that is a saturation temperature. Only superheated steam has got more temperature, that is more than saturation temperature. So in the problem he want the final temperature of the steam after throttling, therefore we have assumed final condition is also superheated, therefore I have taken superheated steam. See here, so H sup 2 formula I have taken. So H sup 2 is equal to Hg2, direct value from the steam table for the second pressure, Cp T sup 2 minus T sat 2. So this value I have in the steam table, 2.2 is given, and T sup 2 we have to find, that is the final temperature of the steam after throttling, and T sat 2 is this much. By simplifying, I have H sup 2 is this much, 1788 point plus 2.2 T sup 2. H sup 2 is not known. This is actually like a equation like this one. Now for throttling process, what is throttling process? Enthalpy before is equal to enthalpy after. So in this problem, before is superheated, after also superheated, therefore H sup 1 is equal to H sup 2. H sup 1 we got in the previous relation. See here, 2963.8 we have H sup 1. Now H sup 2 is in the form of equation, that is 1788 plus 2.22 T sup 2. By simplifying this we have T sup 2 is equal to 534.4 Kelvin. So like that you should find the temperature after throttling. So this is on superheated steam. So like this the simple problems will come on a throttling process. So this ends the processes, that is 7 processes: constant volume, constant pressure, after that constant temperature or isothermal, then we gone to adiabatic, hyperbolic, polytropic, and lastly throttling process. So the next topic is a very important topic, and you will get around 15 to 20 definite marks in the examination in part 3, that is vapor power cycles. Okay, vapor power cycles are similar to thermodynamic air cycles. That means in unit 2 we already completed this air cycles, Otto cycle, diesel cycles, and like that. So similarly this thermodynamic vapor cycles are also similar to air cycles, except the working substance, which is steam in this case. So that means steam is a working substance in vapor power cycles. That steam may be dry steam, wet steam, or superheated steam. Any steam you can use in these cycles. The different types of vapor power cycles are